when a heated object is placed in a cooler environment, it'll start to cool off, obviously. And it turns out that the time it takes to cool off, it'll be decreasing exponentially over the course of that time. So down here we have an equation called Newton's law of cooling, as in Isaac Newton, that represents how long it will take an object to cool off. Now it's kind of a complicated equation. It's got a bunch of variables in it, so let's take a note what each one represents, and then let's do our question with it. So capital T, the big T, represents the surrounding temperature, so usually of the air, but of whatever the surrounding environment is. That is going to represent the temperature around in the room. The U sub O is going to represent the initial temperature of the heated object. So how hot is that thing that you place into the environment? E is of course just E. K is going to be a negative constant in this case, representing how our heat is decreasing over time. And then the lowercase t is going to be time, whether it's hours, minutes, or seconds, whatever. U of t over here just represents our temperature after a certain amount of time has passed. So lots of t's, lots of u's to take a look at. Let's have this formula handy as we start to set up our equation so we can model how long it would take to cool off. So in our example, we're handed a hot cup of coffee. The cup of coffee that's handed to us is 160 degrees Fahrenheit. That represents our initial temperature of the heated object. So that's going to be U sub O when I plug this in. The coffee shop has an air temperature of 72 degrees. That's the temperature of the surrounding environment. So that's capital T in this case. To answer our first question then, they ask us to find K, that constant, if after 3 minutes, so there's our lowercase t for time, the temperature of our coffee has cooled off to 150 degrees. Well, that represents the U of t part, the sort of answer to my equation, the final temperature in this case. So having all of those variables identified, let's go ahead and get those plugged into our equation. Okay, so I've gone ahead and magically done that for you. Again, have that formula handy and then refer back to what we said each of our variables would be filled in with, what number they would be filled in with, because the equation can be kind of complicated with all those different spots. Notice E is not a variable, E is just that number we've always used, and then K is what I'm trying to find. So let's go ahead and solve this equation. Let's do some simplifying with this. So I'll go ahead and simplify my parentheses. So I end up with 72 plus 88 e to the 3k. I'll subtract 72 next, so 150 minus 72 leaves me with 78 equal to 88 times e to the 3k. Dividing both sides by 88 gets me approximately about 0.8864. And then as we've talked about, go ahead and use the full decimal on your calculator. Like I'm going to write down a rounded answer, but don't round that value on your calculator. Keep the whole thing in there. So now at this point I need to switch over and use some logarithms. To get rid of a base of e, I'm going to take the natural log of both sides. Well, once again, try to avoid having that part rounded. Do the natural log of the full thing on your calculator to be as accurate as possible. That works out to be about negative 0.1206 equal to 3k. And once again, use that full number on your calculator. So then as this last step, when I divide by 3, I'm being as accurate as I can, and that constant comes out to be about negative 0.0402. And as we said in the beginning of this video, that constant is going to be negative to represent that we're losing heat over time. So there's our constant. Now let's use that to answer one more question. Suppose that we need to wait to drink this coffee until it's decreased in temperature to at least 130 degrees Fahrenheit. So my question is, now that we know the constant, let's figure out how long it will take to cool off to that temperature. So the only variable that has changed then will be our final temperature, our U of t number. So this time we want U of t to be 130. So I'm going to start with that. The other variables are exactly the same as they were, other than lowercase t now is the variable because I don't know what the time is and I can plug in the constant. So let's plug in the same exact numbers we used up here. All of those will be exactly the same. So let me go ahead and get those filled in. The air temperature is still 72. The initial temperature of the cup of coffee is still 160 when I'm handed it. And then I'm going to do that times E. raised to my constant, so negative 0.0402, and then times lowercase t for the time. So let's go ahead again and simplify what we can and then solve this to figure out the time. So 72 plus, if I go ahead and subtract my exponents, or subtract my numbers in parentheses, that's still 88 e raised to the negative 0.0402t. Oops. I'll subtract 72 from both sides, so that leaves me with 58 equals 88 e to the negative 0.0402t. Our cup of coffee is going to be cool by the time we're done with this question. Once again, from here, I'm going to divide both sides as my next step. So let's divide both sides by 88. And remember, try to round as little as possible, so use the full number if you can on your calculator. But dividing this gets me 0.6591, and then e to the negative 0.042t. And once again, to get rid of my base of e, I'll need to do the natural log to do that. So let's take the natural log of both sides. This works out to be about negative 0.4169. Again, you can double check me on your calculator, of course. And then natural log of e cancels out, so negative 0.0402t. And finally, dividing by that constant, I get a time that it will take my coffee to cool off of approximately 10.4 minutes.